Well, my name is Luis Calvo. I'm in my final year as a PhD student at the University of Oviedo. My research is carried out within a collaboration between the Hydrogeophysics and NDT Modeling Unit and the UNOSA company. And my work focuses on the thermal influence of geothermal systems on the aquifers where they are placed. To support this, an important part of my research involves field data acquisition in flooded mine shafts across the Central Asturian Coal Basin. We perform vertical profiling along the shafts, reaching depths of up to 400 meters, where we measure pressure, temperature, and electrical conductivity. Pressure data allow us to determine depth and locate the water level, while temperature and conductivity profiles help us understand the thermal and hydrogeological structure of the system. I'll briefly go through the structure of the presentation, first an introduction, then a methodology, then the main results, and finally a few conclusions. Well, on the left of the slide, you can see the location of the flooded mine shafts where we carry out the measurements, as well as the simplified schematic of the internal geometry in the below part. These shafts can reach several hundred meters in depth and include multiple levels. On the right, the main objectives are to characterize the vertical thermal stratification, to analyze the spatial and temporal variability of temperature and electrical conductivity, and to investigate the relationships in order to identify mixing processes of water. I will now briefly move on the methodology. Here in this slide, we can see the proof that we use to make the profiles. We use a swift CTD proof. This div is lowered along the mine shafts to obtain continuous vertical profiles. It measures pressure, temperature, and electrical conductivity. The proof is connected via Bluetooth to a mobile device, which allows real-time visualization and data storage. These setups enables us to characterize the vertical structure of the water column in these flooded systems. Starting with the first result, we can see the temperature profiles for all the monitored mine shafts, 12 in total, for the same date. As you can see, there is a strong variability between shafts, both in terms of absolute temperature and vertical stratification. Some profiles show well-defined thermal layering, with these jumps that we can see at different levels, while others are more homogeneous, suggesting different hydrodynamic conditions. One key observation is that the warmest profiles corresponds to shafts where geothermal exploitation is currently taking place in Barredo and Fondón 1. The presence of thermal jumps and irregularities in some profiles may be related to pumping or hydraulic connections with other mine workings at specific depths. If we focus on one specific example, the Barredo shaft, we can see several profiles taken in that place. On the left, the temperatures profile obtained during our measured campaigns, we observed two distinct behaviors, which are likely related to pumping conditions, as different pumps may be operating at different times or with different flow rates. On the right, we compare historical profiles with the more recent ones, and we can see that a general trend that can be observed over time, but after more than 10 years of operation, the system appears to have reached a relative stable thermal configuration with temperatures between 21 and 23 Celsius degrees along the profiles we measured. In this slide, we focus on the Candín-Fondón system, the other one who has a geothermal power implanted. And here we have 4 interconnected shafts which have been monitored. On the left, we can see that despite being connected, the shafts show very different behaviors near the surface. However, as depth increases, the temperature profiles tend to converge, suggesting hydraulic connection at specific levels. For example, Fondon 1, which is the black line, shows the highest temperature from the surface, as it is directly affected by pumping, leading to enhanced mixing. In contrast, Fondon 2, located just a few meters away, shows a very different behavior. We can see the red lines. It's a different behavior near the surface, indicating that both shafts are relatively well isolated at shallow depths. However, below approximately 150 meters below surface, both profiles become very similar, pointing to a strong connection at that level. Candin 2 shows a more stable profile. It's the orange lines. And it shows a more stable profile with fewer thermal jumps, suggesting a more isolated behavior until deeper levels, where the main connections between shafts occur. And for Candin 1, if we focus on the right graph, we observe that temperature and electrical conductivity, temperature is the red lines are electrical conductivity, the black ones, they are strongly correlated, showing identical thermal and chemical transitions at the same levels. In summary, thermal profiles are temporally stable, but spatially variable. This variability is mainly driven by pumping and hydraulic connections at depth. In interconnected systems, shafts may behave independently near the subsurface, but converge at deeper levels. And finally, temperature and electrical conductivity provide consistent information about mixing processes. Well, that's all. Thank you very much for your attention. And if there is any questions or comments, I'll be happy to answer now or via email.